begin. So yes, today we're doing, so the first story arc of the course, if you will, is differential complex calculus, right? And now we turn to the problem of integral calculus. And so to start with, we do kind of, today's focus is on, today is in some sense a review of calculus 3 things. So today we're primarily focused on integrating functions from the reals to the complexes. All right. And so, and specifically, we're going to talk about, come on, here, I have to find markers. Don't fail me now. So here's definition. If we're integrating, say, let's see here. Goodness gracious. U plus, say, IV dx over a curve, right? Then this is just equal to the integral of like u dx plus I integral of v dx over the curve. So, also we have to talk about partial derivatives, right? So we've kind of already gotten into this, but partial x of, say, u plus iv is also just defined in the natural way like this. So this is how we take partial derivatives of complex valued functions. Here I'm assuming like u and v are functions of x and y. All right. Now, the integrals I wrote at the top, these are the, would you guys recall from Calc 3? I must remind you, Calc 3, we had like a vector field, say f is equal to, say, p comma q, that vector field, right? Maybe use notation like pi hat plus qj hat in your course, perhaps. It's a vector field, right? And then we talked about the line integral of that. Do you remember that? So the integral of f dot dr over the line integral c, that was, let's see, another notation for that was the integral of p dx plus q dy over c, right? That was the other notation. And what was actually the mechanics of that calculation? The way we actually did the calculation was something like integral from, say, t1 to t2 of, p of x of t comma y of t dx dt dt plus q of x of t y of t dy dt dt, right? Or more elegantly, you could just say, well, what this is, it's the integral from, integral over the domain of the parametrization of f of gamma of t times d gamma dot product with d gamma dt dt, right? This was here gamma is a parametrization where the image of gamma is equal to the curve we're talking about, right? So like the picture here is something like, here's your curve, it's oriented, right? It's going from gamma of t1 over to gamma of t2. And this is, what did we call this? This was the line integral, right? Or the contour integral. We usually call it a line integral. What is it physically? Physically, this is equal to the work done. Yeah. This is the work done by F over C, over the curve C. Right. All right? And so that's just a quick review of how we define the line integral in Calc 3. See, because, do you remember, and so just to, so what we mean here, when I have like integral of u dx and integral of v dx up here, what that's talking about, right, is this kind of thing right here. This is the definition. This is integral of p dx over the curve C. And this over here, if you include the integral, this would be the integral over the curve of q dy. Right? So what I'm suggesting is we can talk about integrals of differentials, and we just generalize in the natural way. It's a linear combination of what we already talked about. So like the integral of u dx and the integral of v dx, these we already talked about in Calculus 3, and we can still talk about them here. Let me do an example. Let's see here. Suppose we're looking at C, and let's say that's the modulus of z minus z naught equals to r, counterclockwise, right? So that's a circle, right? And we're going to integrate. Let's see here. I don't know. How about 1 over z minus z naught? Time dx. So I'm going to go ahead and do dx plus I dy here. Oh, I'm sorry, I'm getting ahead of myself here. Let me just say dx. Just a second here. Let me think about my life. No, that's not the kind of thing I want. My bad. So x squared dx plus, I dy there. We'll do that one. So the way you do this kind of calculation is you have to figure out what's the parametrization for the curve. Like we're talking about that circle, right? So, what are the parametric equations for the circle? X. In a complex notation, we could do this. C is equal to z naught plus r e to the it, right? 0 less than or equal to t less than or equal to 2 pi. So that right there I wrote in purple is what I would mean by, that's my gamma of t, all right? So this right here is gamma of t is z naught plus r e to the it, right? So let's see here. So this means x is equal to x naught plus r cosine t, y is equal to y naught plus r sine t, right? That's if you look at the real and imaginary components of that, that's what you got. And for planning on my part, I'm going to have to go back over here. So we're going to do integral from 0 to 2 pi, right? What's my x squared? It's, x naught plus r cosine t. I take that, I square it, then dx, what's dx? Minus r sine t dt, right? You remember these calculations? Yeah. So they still work here. And they're still just a shorthand for what I wrote. I mean, again, these are just a shorthand for this more elegant way of looking at things, but...
So is x naught and y naught like essentially just your t? Like when you're combining to get r to the it?
I'm combining to, what's that again? What'd you say? Minus, I'm not sure.
Oh, never mind.
Okay, I dy was, I should only have a derivative of sine is cosine, so r cosine t dt, all right? And So, oh goodness gracious, this is a mess. Integral from 0 to 2 pi. Should have stuck in my notes, you know. What we got? We've got x naught squared plus 2x naught r cosine t plus r squared cosine squared t. There's a minus I should pull out here. Sine t dt, you know, plus I times the integral from 0 to 2 pi of r cosine t dt. Now what happens, I think this is going to be kind of a boring example. The main point of this example was to remind you how we parametrize a circle, because you're going to need to work problems where you have to parametrize a circle, right? So that's like the big thing. In complex notation, z naught plus re to the it. In real notation, we have x equals to x naught plus r cosine t, y equals to y naught plus r sine t. But the integral here is maybe not that interesting. Integrate cosine from 0 to 2 pi, what do you get? Integrating cosine full cycle, that's 0. If we integrate cosine over a full period, it's 0.
Oh.
If we integrate sine over a full period, 0. If we integrate cosine times sine, well, that's sine 2t. That integrated over a whole period, two whole periods, actually, 0. The only thing that has any hope is this cosine squared, this guy right here. So we've got minus r squared integral from 0 to 2 pi of, cosine squared t sine t dt. And if I make u, probably, equal to cosine t, right, then du is minus sine t dt, but you see what happens, what happens with the bounds. 1 to 1. Yeah, integral from 1 to 1, what's that? It's 0. So, sorry, this example, yeah, all right, anyway. So, 0, yep. So, I need to talk a little bit about curves and terminology here, right? So we, at the start of section 3.1, I'm like, a path is, I use the term path for the parametrization of a curve. So like a path goes from, this is a path, right? Gamma is going from the interval 0 to 2 pi to the complex numbers, right? That's a path in C. We usually work with paths which are not intersecting, so like they don't self-intersect, right? I don't have like gamma, except at the endpoints, right? Like the circle doesn't intersect itself except at the endpoints. A path like that's called simple. If the path begins and ends at the same point, it's called closed. We say that the path is smooth if it has smooth component functions. A continuous path is built by case-wise joining of finitely many smooth paths into a piecewise smooth. So like piecewise smooth could look something like, this, right? And so maybe this is like gamma 1, gamma 2, and, this goes on, right? Gamma n minus 1, gamma n. And so if you take gamma is the union of all these guys, and I really, so in the notes I introduce notation like, I think I use bracket gamma for the image of the curve. I call the trace. So that here C is equal to the trace of gamma in the language of the notes. So I'm using the path is the parametrization. The image of the path is the curve which you're parametrizing, which I think Gamelin calls the trace, so that's why it's in here too. But anyway, this sort of thing is called sometimes called a piecewise, this is sometimes called a piecewise smooth curve or arc. So a arc is formed from the union of finitely many piecewise smooth curves. And if you want to do an integral over an arc, it's pretty clear what you do, right? Like, for example, the integral of, say, p, dx would be over gamma would be what? It would be the sum I equals 1 to n of the integral over gamma I of p dx, right? So you just add up the integrals on each piece, right? All right. So let's talk about what is the integral of p dx. What is it anyway? So in particular here, I want to look at the integral of, say, p dx plus q dy over gamma. And here I have in mind gamma as some arc, but anyway. So, and here p and q are complex. All right, so let's say this is more explicitly integral of, like, say, p1 plus ip2 dx plus the integral of q1 plus iq2 dy, yeah? And if you sort through all the properties are exactly sort of the most natural, unsurprising rules that follow from the definitions. And so like this ends up being the integral of p1 dx plus q1 dy, right? Plus I times the integral of p2 dx plus q2 dy. So what is that? Well, this is, and this is all over gamma. So what you're looking at then is the integral over gamma of, like, p1 comma q1 dot dr plus I times the integral over gamma of p2 comma q2 dot dr. And something students always ask me somewhere in this part of complex analysis is like, what does this mean geometrically? And the answer is, you're asking the wrong question. Like, this is, if you just focus your attention on just the real or just the imaginary part, perhaps we can say what it means geometrically. But you really want to take a more algebraic approach here overall. What's happening here, though, is that this single complex integral of a differential, right? So p dx plus q dy is a differential. The integral of a single complex differential apparently is two corresponding, it's a complex linear combination of the work integral of two different vector fields. Like, it's the work of this vector field plus I times the work of that vector field along the curve. So we get two regular work integrals from one complex calculation, all right? All right. So Green's theorem. Do you guys remember Green's theorem? Ah. So it is important that you read the notes here because I have careful definitions of everything I'm doing in the notes. I'm not writing those all down on the board because I'm trying to preserve more of our class time for examples going forward. I think that will help you guys more. So I'm trying. This is your theorem. 3.1.10. This is complex valued Green's theorem. So we'll review the regular Green's theorem and the proof of this thing, okay? So let's see, let gamma be simple, which means non-intersecting, closed, well, usually non-intersecting. Non-intersecting before the endpoints, okay? Simple means, closed means that the terminal points of the curve, the beginning and the ending points of the curve are the same point. right, closed curve, which forms the boundary of S. All right, in the positively oriented sense. I'll draw a picture here to explain what I mean by those words. That is, S is a subset of the complex numbers, and the boundary of S, in the usual way, is gamma, right? And to be fussy, perhaps I should say the trace of gamma. I mean, I don't know. I'm not going to fuss over that kind of thing too much in here. So this is S. All right, whatever. And the positively, so you take your right hand, right? And you insert, you like the right hand rule is going to go, what, counterclockwise around S. So the positive orientation of S goes like this, right? So this is the boundary of S, counterclockwise. All right? Now, here's the Green's theorem. The integral over gamma of p dx plus q dy is equal to the area integral, the double integral over S of partial q partial x minus partial p partial y dA. And by the way, the integral of a complex, so this is a complex valued function of R2 here. What do I mean by the area integral of a complex valued function? How does this defined? In the natural way, like it's the real part of that function integrated over the area plus I times the imaginary part of the function integrated over the area. So the definition is given right before it in my notes, 3.19. It's totally unsurprising. We'll need to get into, anyway, we'll see the definition at work here in the proof, so let's get to it. So here's the proof. Let P equal to P1 plus IP2 and Q equal to Q1 plus IQ2. All right. Then if we look at the integral over gamma of P1 plus IP2 dx plus, let me not write that again, dummy. I'm just rewriting what I wrote over there, guys, okay? So the integral of p dx plus q dy, what did we figure out? It was the integral over gamma 1 of like p1 dx plus q1 dy, right? Plus I times the integral over, that's just gamma, p2 dx plus q2 dy for those reasons over there. And then, okay, what we're looking at is this is a line integral in the plane, and that is also a line integral in the plane. So by the real Green's theorem, by the ordinary real Green's theorem, this is equal to the double integral over S of partial q1 partial x minus partial p1 partial y dA. That's the Green's theorem. Green's theorem says that you can trade the line integral for a corresponding area integral, where you do the x derivative of the y component minus the y derivative of the x component integrated over the area. This is Green's theorem. And Green's theorem, so that's just ordinary Calc 3 Green's theorem, okay? And do the ordinary Calc 3 Green's theorem on the other piece. So if you understand this, you should be able to tell me what to write over here. So you guys tell me, what should I write over here? Mm-hmm. What goes over here? Uh-huh. Right. Mm-hmm. Right. Now, okay, so then what? Well, this, by definition of the definition I haven't written, but is obvious, okay? This is definition, integral of partial q1 partial x minus partial p1 partial y, that guy, plus I times partial q2 partial x minus partial p2 partial y dA. So this is what I was saying before. It's like the integral of a complex valued function over an area is by definition just the integral of the real part plus I times the integral of the imaginary part over the same area. That's our definition of that kind of integral. And then, look, so these we can also put back together. See, this right here, you can put these two guys together. See this? This and this go together to give us partial x of q1 plus iq2, right? And the other one, this one, and that one come together to give me partial y of p1 plus ip2, except there's a minus outside of both of them, right? See that? There's a minus. So, but this is exactly partial q partial x, right? And this is exactly partial p partial y. That's what we mean by the partial derivative of a complex valued function. It's the partial derivative of the real part plus I times the partial derivative of the imaginary part. So what we have is exactly just the integral over s of partial q partial x minus partial p partial y. Now, when I first read Gamelin, it seemed to me like these sections were saying nothing. They seemed to me like they were saying nothing. See, because I've taught calculus 3 before, and this is in my blood. Like, I see this equals to that, I think that's Green's theorem. But don't be deceived. This is a complex version of Green's theorem. It's built on using Green's theorem 2 times. One in the real part, one in the imaginary part. It's got all that in there. But he has a standalone proof. If you read Gamelin, he proves the complex version of Green's theorem using like a standard Green's theorem argument to show that this result holds. Now, I'm just leaving the proof of Green's theorem to calculus 3 because our time is limited in here. Besides, I'm sure you saw the proof of Green's theorem in Calc 3 here, right? Actually, that does seem likely. I think Dr. Rakovich probably did that. You may have forgotten it, but I bet you he did. You don't know? Ah. All right, let's see here. So,
where did minus pop out? Oh, you turned it into pluses.
yeah, there's a minus here and here. Yeah. All right, so let's move along here. Definition. If h is a complex valued function with, hx and hy continuous. In other words, what I'm saying is, suppose it's a complex valued function where you can take the partial derivatives with respect to x and y, and they make sense, all right? Then dh is equal to partial h partial x dx plus partial h partial y dy. All right? A differential form p dx plus q dy is exact on U, a subset of the complexes, all right, if there exists H from U to C such that dH is equal to p dx plus q dy, right, on U. So I should emphasize at each point on U. Failure for that differential to match up with p dx plus q dy at a single point on U is enough for it to fail. It has to be a global property with respect to U. Okay, so an example. We could have like, oh, I don't know, h of, well, we could use complex notation, right? H of z is equal to like z e to the z. So this is a complex differentiable function, right? What's h prime? E to the z plus z e to the z. Okay, and Cauchy-Riemann equations say what? This is partial h partial x, am I right? And what were the Cauchy-Riemann equations in complex? Remember what they were? They were df, so we could say dh dz is partial f partial x is one way to look at it. It was also minus I partial f partial y, wasn't it? Rather h. Using h here. So let's see here. What would partial h partial y be? No. Partial h partial y would be I times dh dz, right? So like if I multiply this by I get minus I squared, which is 1 on the other side, and I get I dh dz, but that's I times e to the z plus z e to the z. So anyway, what do we got? We got dh is e to the z plus z e to the z dx plus what? I times partial h partial y, which is what? Well, I mean, partial h partial y is this is I e to z plus z to z. Now is as good a time as any to introduce a little bit more notation. So notation. dz, we could call the differential of z, that would be dx plus I dy. Yeah? So check this out. This is actually what? E to the z plus z e to the z, right? Times what? Times dx plus I dy. So it's kind of neat because, in fact, dh is just what? It's actually just dh dz dz. Now, this kind of calculation only is possible if the function you're dealing with is, in fact, a holomorphic function. If you had h, which was not a holomorphic function, right? For example, here's a much easier example. Suppose you had h of, x plus iy equals to x minus iy, right? Then this gives you partial h partial x, partial h partial y, which are what? Partial h partial x is just 1, right? Partial h partial y is minus I, yeah? And so what's dh? dh here is dx minus I dy. It is not equal, and you can't write that as partial dh dz times dz, right? Because, well, dh dz, it does not exist, right? Because the conjugate, complex conjugate map is not differentiable. All right, so moving along here. What theorems do we know about integrals of differentials? Do you remember? So we've talked about Green's theorem. That's one of the integrals. One of the theorems we have about differentials, right? But what else do we know? I will remind you. So this one's an important one. Theorem 3.2.2. So gamma an arc from A to B. All right. And if we have H continuously differentiable near gamma, all right, near the trace of gamma, if you will, then if dH is equal to p dx plus q dy, then the integral over gamma of p dx plus q dy, right, is just equal to h of b minus h of a. It's probably worth our time to go through the proof here because it illustrates definitions which I haven't written out. Here's the proof. So we'll let gamma be going, say, from T1, T2 to the complexes, right? Gamma of T1 equals to A, gamma of T2 equals to B. So let's let gamma be a parametrization of our arc. Now, I'm going to be a little bit lazy and assume that it's just a single arc, single smooth path. The full proof here, you would, look at a linear combination of these results over the arc, and there'd be some kind of like telescoping of the result. But I'm gonna be lazy. If I prove it for a single arc, a single path, you can extend to arcs just the same. What it is?
I'm actually going crazy. This is just the punchline to the FTC, right?
This is the FTC, but this is the complex version of the FTC. So this is FTC for line integrals, but we're doing FTC for complex valued line integrals. So this is not a theorem you saw in Calc 3 because in Calc 3 this was all real valued stuff, right? So, but here it is, p dx plus q dy over gamma, right? Well, that's equal to the integral from T1 to T2 of p of gamma, right, of t, times dx dt plus q of gamma of t times dy dt. Here I'm introducing x and y as the components. Oops, don't need those. Sorry. I guess I usually write the dt once, so let me do that. There we go. So that's just the definition of those. But remember, we're assuming that dH is p dx plus q dy, right? So that means that this p is actually what? It's actually partial h, partial x of gamma of t, dx dt, plus partial h, partial y of gamma of t, dy dt. Which is really just what? So at this point, I guess I should probably write h equals to h1 plus ih2. Right, h is complex values, h1 plus ih2. And so if you look at that, what you've got is integral from t1 to t2, partial h1, partial x, dx dt, plus I, plus partial h2, partial h1, partial x, partial y, my bad, dy dt, plus dt, plus I times integral from t1 to t2 of partial h2, partial x dx dt, plus partial h2, partial y, dy dt. And if you don't mind, I'm omitting the of gamma of t dependence because it's just too much to write. But the point is, those are, by the chain rule of calculus 3, that's d dt. This is straight up d dt of h1 of gamma of t, right? And this right here, go on. Yeah, you asked your question. Go ahead. Right. Yeah, I think if I had been lazier here, so I'm basically reproving the FTC for Calc 3 2 times here. I think I could have gone a different path and used the FTC of Calc 3 to prove this. That would have been, maybe that would have been better. But the point here is we have the integral from t1 to t2 of this total differential. And so what's that? That's h1 of gamma of t2 minus h1 of gamma of t1 by FTC plus I times h2 of gamma of t2 minus h1 of gamma of t1. But that's exactly h1. Well, okay, so you put the h1 and h2 of gamma. Gamma of t2 is b. So what we've got is we've got h of b minus h of a. So like the h of b is coming from this term and this term. And this one is giving me the h of a. But you're right, this is the fundamental theorem of calculus for line integrals, but this time complex valued line integrals. Now, is it always possible to write any p dx plus q dy as the differential of h? In other words, my question to you is every differential form exact? I'm asking about complex ones, but you could ask the same question about real differential forms, of course. So the answer is no, right? So here's definition. One way to look at that is p dx plus q dy, right, is independent of path, right, in U, which is a subset of C, if what? If the integral, let me call this thing omega. If the integral over gamma 1 of omega is equal to the integral over gamma 2 of omega for, I'll draw a picture. Here's U, here's my points, A and B, right? And this is, gamma 1, and here's gamma 2. So gamma 1 and gamma 2 are coterminal paths. They have the same starting and ending points. So if it doesn't matter how you get from point A to point B, the integral of omega is the same no matter what, then that's an independent path form, right? And there's an easy theorem. Well, it's not so easy, I guess, but part of it's easy. Theorem 3.2.5, which is that the integral, p dx plus q dy is independent of path in U if and only if the integral over gamma of p dx plus q dy is equal to 0 for all simple closed curves in U. So, and a simple closed curve, I should mention, this we'll later just call a loop. So if you want a nicer, an easier term for that, it's a loop. Yeah. Now, so this one's relatively easy to prove. Like it's essentially just a picture is the proof here. So, and I need some condition on U. For this to make sense, U has to be a set which is big enough to support these ideas, right? So I think that the preamble to this theorem really should be, let U be a domain. Well, let's let U be a region. It should at least be a region. Maybe a domain is I probably want a domain. What's the difference between domain and region? Remember, domain means open connected set. A region could be like an open connected set plus some of its boundaries. I don't really want to fuss with the boundary of the region, so let's just say domain. So here's the picture, right? So independence of path, right? So here's our universe, right? U. So you pick your 2 points, right? And so independence of path, so you need to pick two paths, right? Like that. And maybe like that, right? Why should that, so these are, let's call this thing omega for the sake of doing less writing. So we have that the integral, we're assuming, let's go this direction, all right? We have that the integral over gamma 1 of omega is the integral over gamma 2 of omega, right? We'd like to show, and this is true for all, right? For all such gamma 1 and gamma 2, right? For all loops. Now, what we want to do is do what? We want to show that the integral around a loop, listen to me, loops, no, paths, yeah. Sorry, paths from A to B like this, right? So, all right, so what do I need to do? Here's my universe. I need to show that the integral around a loop is 0, right? So you pick a loop. Whatever. It's got the same starting and ending point, but it doesn't intersect anywhere in between, right? Why should that integral be 0? Well, look at this. Pick any other point over here, right? And so if the loop, let's call the loop gamma, right? If the loop is gamma, so then gamma is equal to gamma up union gamma down, right? Gamma up, gamma down. And what can you see? Well, the integral over gamma of omega is the integral over gamma up omega plus the integral over gamma down. But what can you tell me? This is equal to what? Integral over gamma up minus the integral over minus gamma down. So what's minus gamma down? So here I need to point out that all these integrals we're defining, they're oriented integrals. Yeah, we're done. And so minus gamma down goes the other way. See, like this? But notice that the integral over gamma up and the integral over minus gamma down, those are equal by the assumed path independence. So that shows you that these cancel and you get 0. But the loop was arbitrary, so that proves that the integral on any loop is 0. And you can pretty much reverse this argument. To be fussy, you could have intersections, so you have to divide it into subloops, and there's actually some fussy things to do here, but anyway, that's...
So you're saying a path independent can be seen as a loop?
I'm saying independence of path is equivalent to integral over loops being 0.
Okay.
Next time, we'll talk about the other thing, which is that it's also equivalent to the existence of a potential function, right? And then that will tie into the exact differential forms. So anyway, I shut up.